All right, so this is the beginning of Lecture 4. Lecture 4 covers Chapter 15, which is basically an introduction to acids bases. If you have taken another chemistry class previously, in terms of Chemistry 130, you probably already saw a lot of this material, so this could be a review for you, and that's okay. In terms of this chapter, Part 1 will cover Arrhenius models and Bronsted Lowry models of acids and bases. There is one more model called the Lewis model that will be covered in the next video. So, before we begin, it is important to remember three terms. A proton in this chapter is referred to as H+. A hydroxide is referred to as OH-, and hydronium is H3O+, and hydronium is just when H+ reacts with water. Okay, it does immediately form H3O+. Okay, so that is what we call a hydronium ion. All right. So in terms of acids and base reactions, before we begin, let's just do a very basic comparison of acids and bases. Acids are usually sour to the taste. Examples are lemon juice and vinegar. A common acid that we have used in lab a lot is HCl. Okay, and with the cabbage indicator, it often turns red or pink. And when we talk about the cabbage indicator, what we're saying is we take some purple cabbage, we blend it up in the blender, we filter out the fibers, and we end up with this purple juice. Okay, and so this purple juice is at pH 7, but when you add an acid to it, like lemon juice or vinegar, you will end up with something pink or red. Okay, this is obviously the neutral pH 7. Okay, and then if you have a base, oftentimes it will be yellow like this. So these are basic solutions. Okay, and basic solutions are examples are ammonium and household cleaner, and it turns yellow or green with the cabbage indicator. And we'll cover this at a later time. I should have gotten rid of this on this slide. We will cover that definition at a later time in this video. All right. So in terms of the first model that we're going to cover, it is the Arrhenius model of acids and bases, and it was discovered by a savant Arrhenius, and he is the one who recognized in the early 1900s, actually the late 1800s, the essential nature of acids and bases. And so he basically defined an acid as something that produces hydrogen ions, or H+, in an aqueous solution, and a base is something that produces hydroxide, or OH- ions, in an aqueous solution. So an example is HCl. Of course, we do know HCl is a gas. So if you bubble HCl gas into water, okay, what will happen is that the HCl will dissociate and form H+ and Cl-. Because it does form H+ in aqueous solution, we like to call HCl an acid. Okay, NaOH is another great example of an Arrhenius base. NaOH solid, when you dissolve it in water, it forms Na+ and OH- as separate ions in solution. And because it does produce OH- or hydroxide in aqueous solution, NaOH is called a base. Okay, so under this model, it's very simple. Arrhenius won the Nobel Prize in 1903 for his work on ions in solution. All right. Now, in terms of acids and bases, Arrhenius acids do donate H+, but it is important to remember that a free H+ never remains unreacted in water, but immediately forms H3O+ in solution. Okay, so for example, if you have HClO4, you put it in water, it immediately forms H+ and ClO4-. So these two ions are floating around in solution. Okay, but remember, this is in a beaker filled with millions upon millions of water molecules. Okay, and so H+ will immediately see a water molecule and say, oh, we need to form H3O+. Okay, so really, once HClO4 dissociates, it immediately forms H3O+ and ClO4-. There really isn't any free H+ in solution, because the moment H+ is produced in solution, it immediately finds an H2O and forms H3O+. This is almost an immediate situation. Okay. So for simplicity, oftentimes we don't write H3O plus, we often write H plus, but when we write H plus aqueous, we really do mean H3O plus. Something to keep in mind as a footnote moving forward in this chapter and the next chapter. So the next model that we're going to cover is called the Bronsted-Lowry model, and it's named after two scientists, Johannes Bronsted and Thomas Lowry. And they developed a more inclusive model in which they defined an acid as a proton donor and the base as a proton acceptor. Okay. Notice in this particular case, it's almost the same definition. It basically means an acid will give away an H plus or can donate an H plus, whereas a base can accept H plus. Okay. So let's look at an example. You have HCl as your acid and water as your base. What is going on in this reaction? Let's take a look on a molecular level, okay? So this is your H plus. This is your Cl minus, okay? It reacts with water and donates an H plus. So this hydrogen actually finds its way onto one of the waters and actually forms H3O plus. Okay? What's left over is, of course, your Cl minus. So that's what we write here. We say HCl reacts with water to form H3O plus and Cl minus. Okay? Notice the HCl does donate an H plus. Look at this. It had an H plus. Now it doesn't. Right? So it has donated an H plus. So it's an acid. Okay? Water, okay? I'm going to erase this little H that I've drawn here. Water, okay, was H2O. It accepted an H plus and became H3O plus. So because the water accepted an H plus, we call this a base. Okay? So this is the newer model of acids and bases, and we basically can include more things as bases, right? So like, for example, NaOH was your old model, NaOH, right? And we said it donates OH minus or produces OH minus in aqueous solution. So this is a base, okay? In this new model, NaOH can still be a base, right? Because think about it, NaOH, if you have H plus NaOH, okay? The OH can accept the H plus, right? And it forms Na plus and water, right? H plus and OH minus together forms water, right? So the OH does accept H plus. So in this case, NaOH is still a base. Okay? It just includes more things, and we're going to see what we're talking about in just 1 second. Okay? So before we move on to, what other things are bases in this Bronsted-Lowry model, let's look at in depth what is going on when H2O reacts with HCl. Okay, what is happening is that the lone pair of oxygen on water forms a bond with the H plus of the HCl. So I've drawn a Lewis dot model, okay, a Lewis dot structure of water, and notice it has 2 lone pairs. Okay, one of the lone pairs will form a bond with the H, okay? So there's a bond being formed, and again, this is the bond that's being formed, okay? And these electrons here will actually move on to the chloride. These electrons here moves onto the chloride and now exist as a lone pair, okay? So really, this gives you your H3O plus and your Cl minus, okay? So really the Bronsted-Lowry model, again, we're going to define an acid as a proton donor and a base as a proton acceptor. So in the reaction, there is an acid and a conjugate acid that is formed. So if you consider the forward reaction, the acid I changed this slide and I didn't change this, sorry. The acid is HCl, okay? And so therefore, HCl reacts with water to form H3O plus and Cl minus, okay? In the reverse reaction, okay, so let's say that these are the products, okay? If you reverse it, these become the reactants, okay? In this particular situation, let's look at the reverse reaction, right? H3O plus reacts with Cl minus to form water and Cl minus, right? So again, the proton donor in this case is your H3O plus, right? It donated a proton to Cl minus to form HCl, and after donating a proton, it becomes H2O. So in this particular case, the acid is your H3O plus, right? So therefore, we call this a conjugate acid because it is an acid in the reverse direction, okay? So really, what we like to say is this is your acid, this is your conjugate. Conjugate acid. Okay? And in fact, this is your base, and this is going to be your conjugate base. Okay? Why is this the conjugate base? It's because Cl minus, okay, it is a proton acceptor. It accepts an H from H3O plus to form HCl, so it is the conjugate base. So as a recap, okay, under the Bronsted-Lowry model, we have HCl as the acid, the H3O plus is the conjugate acid, H2O is the base, and Cl minus is the conjugate base, okay? And so what we have here is a conjugate acid pair where HCl and Cl minus, this is your acid, this is your conjugate base, okay? And then H2O is obviously your base and its conjugate base pair. H3O is your conjugate acid. Okay? So you will have to label acid base, conjugate base in the homework. So just make sure you know how to do that. We'll do some example practice problems. Okay? So we're going to look at the Bronsted-Lowry model and identify what is the acid base, the conjugate acid, and the conjugate base. So H3O plus reacts with NH3. Okay? Notice this hydrogen is going to get donated to the NH3 to form NH4 plus. So because this hydrogen is donated, okay, we say that this is the H plus donor. Okay? And NH3 obviously accepted an H plus, right? Okay, to form NH4 plus. So remember, if you donate H plus, you are an acid. So H3O plus is your acid, and NH3 is your base. Okay, and since this is the acid, the conjugate base pair, remember, an easy way to think of this is just to reverse the reaction. NH4 plus is actually donating the H2 water to form NH3 and H3O plus. So this is going to donate H plus. So this means that this is the acid, but it's the conjugate acid. Okay, so NH4 is the conjugate acid. Okay, making the water a conjugate base. Okay. And again, these are your pairs in terms of your acid and your conjugate base, and then your base and your conjugate acid. All right, another exam-like question is again to identify the acid base, the conjugate acid, and the conjugate base. So these are great multiple choice questions. I could say, given the reaction below, what is the acid, or what is the conjugate acid, etc. Okay. So for example, NH3. NH3 reacts with water to form NH4 and OH minus. Okay, so let's keep track of what is happening here. One of the hydrogens is going onto the NH3 to form NH4, right? And because it's losing one of the hydrogens, it forms OH minus. So this is actually your H plus donor, and this is your H plus acceptor in terms of the donor and acceptor, right? Because the water is donating H, it is the acid, and NH3 is your base. Okay. As a result, this NH4 is your conjugate acid, and your OH minus is your conjugate base. Okay. Last but not least, HCl and NH3. Again, notice, and this is a little bit tricky, it actually donates H plus, and NH3 actually accepts H plus. Okay, so the immediate result of that is you get Cl minus and you get NH4 plus, right? And these two actually react together because one is an anion, one is a cation. it reacts together and it forms NH4Cl. Okay, so really, again, the HCl donates, so it is the acid, and the NH3 accepts the H+, so it is the base. Okay, and in this particular case, there is no conjugate acid, conjugate base, because it does form just this molecule here. Okay, if you really wanted to, you could say that the NH4 is your acid, your conjugate acid, and your Cl- is your conjugate base. Okay, and together they do form NH4Cl. All right, so let's look at some examples from your book just to get just a little more practice. And again, you're trying to determine what is the acid base and the conjugate acid base pairs. And again, we're following the H+, because remember, the acid always donates H+. So if you can figure out who's giving away the H+, you can figure out what is the acid. All right, so HCO3- reacts with HF. Okay, so let's look. It forms F-. So because of that, we know that this is donated or lost, right? So this is donating. So therefore, HF, in the first one, the HF is the acid. Okay, and the HCO3- is the base. Okay, because it does accept H+. Okay, and in terms of the conjugate, okay, this is going to donate an H if you reverse the reaction. So therefore, because it's going to donate, that is the conjugate acid. So H2CO3 is your conjugate acid. Okay, and therefore F- must be your conjugate base. Okay, let's look at B. Again, HCO3- or bicarbonate is reacting with OH- to form water and CO3 2- or carbonate. Notice in this case, this is actually donating an H+, right? To form this, right? So it's losing the H+ or donating the H+. So really your HCO3- in this case is your acid, okay? And your OH- is your base, okay? And notice the reverse reaction, this is being donated to form OH-. So in the reverse reaction, your H2O is going to be your conjugate acid because it is donating the H+. And your CO3 2- is your conjugate base. Okay. Notice in this example here, I'm going to use a different color here, your bicarbonate is your base. And notice here, bicarbonate is your acid. Okay. Bicarbonate is something that we call a buffer. Okay. It can act as an acid or a base depending on the situation that you put it in, or the solution that you put it in. Again, we're going to look at two chemical reactions, and for each of the following reactions, again, we're going to identify all of these things in terms of the acid base and the conjugate acid base. So again, this is an example of a molecular problem where you're looking at molecules and seeing if you can understand what we're talking about when we write chemical reactions. So we might encounter some of these kind of problems as multiple choice questions. So again, you're just going to follow the H. So remember, this is your H+. Okay, it's going to be attached to the water to form H3O+. Okay, and obviously it's lost this H+ to form this carbonate. So really, this is your acid. This is your base. And this is your conjugate acid, and this is your conjugate base. Okay? So this forms one pair, and this forms one pair. Okay? Notice here again, this is the same molecule, but it is acting as a base instead of an acid because this is your H+ that's being donated, and now the F is naked or without an H. Okay, so this is your acid, and this is your base. Therefore, this is your conjugate base, and this is your conjugate acid. Okay. All right. Another way you could ask the same kind of question is to decide, is it an acid or a base, and identify the conjugate acid or base. So HF is obviously an acid. Okay. it will donate an H plus, okay? So therefore the conjugate base is going to be F minus, right? Okay, because if you donate an H plus, okay, then therefore all that's left is your F minus, okay? Actually, let's just write it like this, okay? NH4 is, again, an acid, okay? So therefore the conjugate base is your NH4 minus an H plus, so therefore it's NH3 instead of NH4, and you're dropping more negative in charge, so it becomes NH3, no charge, okay? So ClO4 minus is a base. It can't be an acid because there's no H plus, so therefore the conjugate acid has to be adding an H plus, so HClO4, no charge, okay? One very easy way of doing the conjugate acid or base is to just write the equation, right? So in this case, this is a base. So ClO4 minus plus H plus should give you HClO4, and you're adding the charges because this is plus and minus, so this is neutral. Okay, same thing here, NH4 plus, okay, it gives away an H plus, so what's left over is NH3. And again, it must be neutral because neutral and plus, if you imagine this arrow as an equal sign, must equal plus. So that's why, again, this is neutral. Okay. NO3. NO3 is obviously a base because it has no H plus. So if it gains an H plus, okay, so it's a base. Therefore, you're going to get a conjugate acid of HNO3. Okay. H3O plus is obviously an acid, okay? And again, we can write an equation for acids as well. H3O plus gives away an H plus and results in a leftover water, okay? So your conjugate base would be your water. There is something called an amphoteric species, and we talked a little bit about this when we talked about bicarbonate. An amphoteric species or a substance is something that can behave as an acid or a base, okay? So in particular, NH3 reacts with H2O to form NH4 plus and OH minus. In this case, the H2O acts as an acid, right? It accepts an H plus. Sorry, it donates an H plus. It acts as an acid because it donates H plus and ends up as OH minus, right? But if you put H2O with something like acetic acid, it will actually donate an H plus. Sorry, this is incorrect. It will actually accept an H plus, okay? And so therefore it actually forms, let me rewrite this, I don't know, I think it's a copy-paste error. It actually forms C2H3O2 minus plus H3O plus, okay? Because it accepts an H plus, we call this a base, okay? So notice in the first reaction, H2O is an acid. In the second reaction, H2O is a base, okay? So water obviously can serve two functions depending on what it's mixed with, okay? That's why water is what we call an amphoteric species in terms of its naming, okay? In fact, water can, in fact, form itself an acid-base reaction. So a water molecule can react with itself or another water molecule, and it can form what we call H3O plus and OH minus, okay? So how does this happen? If you have two water molecules, one acts as an acid, one acts as a base. This one acts as an acid, it forms a bond here, okay? So this is a forming of a bond, okay? So it forms this new bond here, and this is H3O plus, okay? These electrons actually go onto the oxygen to therefore form a lone pair, and it forms OH minus, okay? So water is actually reacting with itself. One water molecule acts as an acid, the other acts as a base, okay? And therefore you form H3O plus and OH minus. Now, this reaction doesn't happen a lot in pure water. This dissociation doesn't occur very much. In fact, in the later on in the chapter, we're going to talk about this a little bit more. In pure water, the concentration of H3O plus and OH minus is 1 times 10 to the minus 7. So that's really 0.0000001 molar. Okay, so there's very little of these two ions in solution in pure water. But this is what we call a autoionization reaction. Of water, because it can react with itself, meaning auto. That's why it's called autoionization, because it forms ions just by itself with two water molecules. Okay, so in terms of this video, the main takeaways are this. They identify what is an Arrhenius acid and base, and more importantly, you should be able to identify what is an acid base with Bronsted Lowry model, and in particular, it's very important to be able to do these kinds of problems where you identify the acid, the base, the conjugate acid, and the conjugate base in terms of the Bronsted Lowry model. So on the homework, you will be asked to do problems like this, where you have to label the acid, the base, the conjugate acid, and the conjugate base. Remember, the acid forms the conjugate base, and the base forms the conjugate acid. If you remember this slide, it will help you a lot in terms of how to label these correctly. All right, this is the end of video 1 in terms of this lecture on chapter 15.